Hello, my name is Binghong. I'm an undergraduate student from the Hong Kong University of Science and Technology. The paper I'll be presenting today is titled Research on Turnout System Diagnosis Based on Group Decision Making. High-speed railways are playing an increasingly important role in terms of transportation in China. By 2022, the high-speed railway system in China has reached a total length of over 40,000 kilometers and undertakes more than 60% of the country's railway passenger service. Naturally, such a vast system calls for a strong safety measure, and among various safety-crucial railway systems are turnouts. They are vital to railway systems as they can guide the train's direction and let the trains switch from one track to another. If they are not in the correct position, trains can derail or in worst case, collide with another train from the opposite direction. However, the fault diagnosis of turnouts today still rely on visual inspection carried out by experienced workers. Here shows two current versus time curve generated by the turnout motors. The left one is a normal curve, while the right one shows a broken diode. You can see that sometimes the faulty curves are really similar to the normal curves. To make things worse, even a single turnout can generate hundreds of these graphs in a day, and inspecting all these graphs can be painstaking for the staff, which may lead them to ignore some of the danger signs. Researchers have tried different methods to automate or assist the turnout fault diagnosis procedure, and they have gotten some promising results. Yet the previous works mainly focus on a single algorithm and may encounter some inherent drawbacks. For example, artificial neural networks require a large database for the training procedure to improve its accuracy, which may sometimes unavailable due to the fact that turnout faults are low probability events. To deal with this issue, we propose a new turnout fault diagnosis method based on group decision-making algorithm and combining three different classifiers, namely the deep neural network or DNN, the naive Bayes filter, and the k-nearest neighbor algorithm or KNN. By doing so, we hope to improve the diagnosis accuracy and moreover its sensitivity to malfunctions of turnouts. The diagram shows how we tackle this problem. We first feed the data into the three individual classifiers and let them make their own decisions. Then we regard each of the classifier as an expert and gather their suggestions in a group decision-making manner. In this research, we specifically use an algorithm called one-vote veto, which means if any one of the three classifiers thinks there's malfunction of turnouts, then the final classification of this case will be a fault. By doing so, we're using the concept of diversity to minimize the probability of letting go any fault cases. As safety is always a primary concern of railway systems, it is sometimes acceptable to generate a few false warnings if the missing report rate can be reduced. We also carry out experiments to verify that the group decision-making algorithm can achieve the objectives mentioned previously. We feed real-life turnout dataset to the three individual classifiers as well as our algorithm and observe their classification results. To be specific, for KNN, we set the number of neighbors to 3, and in DNN, we've constructed two hidden layers, each containing 136 neurons. Five-fold cross-validation is also adopted in the experiment. The results are shown in this table as well as in the graph. In the graph, the 3 bars for each algorithm refers to its accuracy, selectivity, and recall, respectively. Accuracy refers to the algorithm's overall diagnosis accuracy, while selectivity measures the ability to identify normal cases. And recall rate, which is our main focus, measures the algorithm's ability to identify a fault case. The experimental result shows that our algorithm achieves relatively high and balanced performance in all the 3 categories. Its overall accuracy is almost the same as the best one, while its recall is higher than any other individual algorithm. So it is safe to conclude that our algorithm indeed achieved the objective of reducing the missing report rate while at the same time maintain a high overall diagnosis accuracy. So it can be used to assist the turnout fault diagnosis procedure in real life. Future work may be on carrying out data preprocessing to extract features from the samples, like their mean value, variance, and time span, and feed these features instead of the raw data into the classifier. And by doing so, hopefully, this can further improve the diagnosis performance of our algorithm. And that's the end of my presentation. Thanks for your attention.